Hi.
Yes.
Brilliant. Perfect. Thanks, Dave.
Yes. Okay.
So I will give you the introduction and then we'll make a start. So Dave Kelf is CEO of Breker Verification Systems. He's a well-known EDA industry participant, having run Cadence's verification marketing, driven Synopsys' verification strategy, and run marketing for Code Design, SystemVerilog, Novas, Verdi, and others. Now he is CEO of Breker, focused on SoC verification and SystemVIPs. He has a solid engineering background, has performed many ASIC designs, and holds a microelectronics MSc from Brunel University. The title of his talk is Aligning Systematic Verification Requirements and Test Bench to Drive Random Vectors and Automated STL Production. Over to you. Thank you, Dave.
Yeah, thank you, Mike, and good morning, everyone. So firstly, that was a great presentation by Hans. So really enjoyed that. It's a great description of where we're at with ISO 26262, functional safety in general. And hopefully what we're going to talk about here will lead on a little bit from that and show just one small part of, a possible solution for part of that. A little bit about Breker. I'm not going to do any marketing here, but basically what Breker's all about is taking models of high-level scenarios and specifications of designs and generating tests for the entire verification process, starting at the virtual platform level right through to post-silicon, and using synthesis to do this. And something we've done is created the library of SystemVIPs, and one of those library elements is indeed a solution around automotive ISO 26262. Oops, sorry. We've done this in conjunction with 3 or 4 other fairly large OEMs, automotive OEMs, and what we've been trying to do is figure out an automation method for covering more the systematic part of the ISO 26262 flow, which is the rigorous verification part, if you like. But this does bleed over to the random fault injection part, and even STLs and other aspects of this as well. So back to part of a slide that Hans just showed us, the famous V model that is used in ISO 26262. The idea behind this model, a simpler version, is on the left-hand side, you see a system level specification, which is then decomposed into requirements, development plans, implementation plans, and then moving up the right-hand part of the V, the verification of those elements of the systematic verification process. So the idea is that we have a verification element for every part of the sort of development and implementation plan, and then we test coverage against each one of these. So today this is a very manual process, of course. There's a lot of paperwork involved, and the engineers have to plow through reams of requirements and implementations to generate tests which actually exactly match the original specification. And it looks something like this at a very high level, where you would start with a requirements specification. You would, from that, and that would end up with a series of requirements, if you see this blue box. That forms an implementation plan, which consists of a number of different features, and then a verification plan, which contains a number of verification goals, which have to exactly match those features. And then on top of that, then of course you need a coverage mechanism for each one of these different goals to show you've actually really tested it. So you end up with this kind of looping diagram, if you like, of different plans with a verification section in the middle, where we can feed back into the requirement specification and make sure we've got the kind of coverage that we need to demonstrate that the design has been properly and fully tested at a systematic level. And by the way, I think this slide was one of yours, Mike. I plagiarized it from somewhere. I'm pretty sure it was a presentation you gave like quite a few years ago. So credit where credit's due. So, sorry?
You recognize it, so thank you.
Yeah, no, absolutely, yeah. So basically the question is, looking at this plan, and this is a very simplified version of what you have to go through. Anyone in the audience who's done this will know exactly what I mean. What we want to try and do is see if we can automate at least some parts of this V-model process with the idea of creating models that go down the left-hand side, using those models to create tests coming up the right-hand side, and then performing coverage tests, which are very, very accurate and depict exactly the specifications that we're trying to develop here and trying to test. So what I want to do is go through an example of how we might want to do this. So looking at this V model, what we could do is create a model of aspects of these requirements. And once we create this model, use synthesis technology to actually drive the test vectors for this for a range of different potential engines, simulation, emulation, even formal, and pick out using constraints specific areas that match the requirements that we want to test, and then use those to generate the coverage reports that allow us to prove that we've actually tested these things. So this is the general idea, and the best way of illustrating this is to show an example. So this is a very, very simple example. It actually came from a generic report from one of our customers, but it's public, and it is the kind of documentation they need to test, in this case, an electronic steering control lock in ESCL. So you can see at the top left a basic safety goal, which is essentially saying you can't lock the steering column when the vehicle's actually moving. And part of this context is when the ignition is on, but when you're looking at something like this, you might want to decide what happens when the ignition is off and there's no key. You need to make sure that there's some independent mechanism to actually show that the vehicle is moving, just moving down this sort of chart, and so on and so on. So, again, this is a little tiny subset of the kind of documentation that a verification engineer in this space needs to look at and say, okay, how am I going to create a test for this? So what we're able to do is create a model. This model in the Breker context can be written in the portable stimulus language or in C++. But it's a very simple graph where you take your ESCL, your electronic steering control lock, and you check if it's active or inactive based on a series of inputs. And in this case, we just pick the ignition switch, some arbitrary movement sensor, which checks if the car is actually moving or not, or if it's still. And also, we may want to check to see if the key is actually in the lock to make sure the ESCL is on or off. If the key's not in there, of course, the ESCL should be on to make sure that the car can't be stolen, which is the real purpose of this. So we have this simple diagram, and this pretty much reflects that specification I showed you on the previous page. And what we can do, to meet this requirement, we can put a constraint on this to say, okay, the ESCL should be inactive if the ignition is on and if the movement is detected. So regardless of if it was active before, when the car was still, if the car starts moving, it should switch to inactive. And we want to test to make sure that this actually happens. Okay. And this is how we might go about this. So we take this kind of a graph model, we run it through the synthesis tool, and we can apply coverage constraints to this to make sure that we're testing other aspects of it. We run the synthesis technology and generate tests for this. So the idea here now is to essentially make sure that we can take this high-level model and provide a very broad range of tests for this, all fairly automatically, and then apply them to whichever part of the verification process we're working in. Of course, this is a very simple component of a much, much bigger system. But the nice thing about these graph models is having created these simple components, you can then start to add to them. So what we can do is take a much larger specification model. We can start to bring in here, like the alarm system in the car, the door lock as well, and start connecting up a much bigger, broader graph. And you can imagine that these things can get very, very complex, but it's a much easier way of describing the very complex requirements type documentations that we get from this, from this process. Once you've got a very large graph, now we can perform a lot of different checks and make sure that this is working correctly. So the way that we generate tests is essentially to walk this graph. So we walk down the graph and we can generate a test for each one of those paths that's shown on the graph. And as you can imagine, as you add a new block to the graph, you're doubling the number of tests and the number of variants that we're generating here. So we can do things like check the reachability of this. So this basically provides essentially a large state machine, if you like, or a large series of tests, not unlike what you would expect in a formal verification tool, which decomposes the design into its state space in time. This is decomposed in the model, and we can do things like perform reachability on this. So what we're able to do is check all the paths in that design in a hierarchical fashion, work through the diagram and see if there's any parts of this which are unreachable. I guess an example could be something like, can we actually test, given the constraints that we have, that if the ignition key is actually in the control lock, can the control lock be controlled properly, for example? Is that a reachable test based on this specification graph? So we can perform different tests like this. And of course, as we do this and generate these tests, we start to generate a very large number of actual tests that can be applied to simulation. This was an actual real example. We're quite surprised to see the number of tests that were generated. So what we're able to do is then go in and constrain this so we get it down to the very specific tests that we need to match that requirement specification. And then the other thing we need to do is then check the coverage of this. So if we have if we just run the model and synthesize the tests, we'll see some kind of coverage report like this, where you have some red parts which basically say these paths have not been tested. What we're able to do now, given that we have this model and we understand all the paths that are in there, is we can add a full coverage closure element to this, which basically tests all these different paths in the graph there. Make sure that all the paths have indeed been tested, which you have to do with the systematic verification, and relay them back to the actual original requirement specification or implementation plan. So you can see here then that what we're able to do is close the coverage on that model itself and relay this back to the original requirements. And this whole thing is being done at kind of the specification requirement scenario level. So you notice that we haven't been talking about design coverage here or functional coverage on the actual design. What we've been talking about is just covering the actual specification and the requirements in that V model. But of course, what we're doing is generating tests, and those tests can be applied to the design, and we can use other coverage models to make sure that the functional coverage is also being tested thoroughly. And we can extend this. So something Hans mentioned is the idea, not just functional testing, but performance testing, and of course, safety testing. So what we could do is we could take a series of tests, for example, a simple set of tests, and run them in series. We could talk about some of these tests may be combinatorial in nature, which is what we sort of see in UVM today, right? If you write a functional model, you're usually testing an assertion of several different components. Are they operating correctly at the same time? We can also run sequential coverage, which is checking that a sequence of tests are correctly working and providing the right validation. But what's most interesting, if we actually look at concurrent tests. So if we take these different tests and we spread them across a number of different actors, should we say, masters, CPUs, or I/O in a design, and the memory or other components, what we're able to do is check concurrent coverage. That is, set constraints to make sure that multiple tests that are running together, as in a real situation in a car, the critical ones that are running together can actually be really tested thoroughly. And we can do that using components, the memory, for example, and other resources on the SoC, and to really get a coverage display, which gives us a sense of not just the functional coverage, but also performance coverage too. So in this situation, what we would do is generate tests in the top right-hand window there, which are all the same length. But after they've been executed on the design, now we can check to see how long some of those tests took. And some of them might be quite short. Others might actually become very long, and you can check for bottlenecks and generally making sure that all these tests have actually been exercised together correctly. So this is a very powerful notion and works very well in the systematic world to make sure that the whole set of requirements, because what will happen is requirements will be layered on top of other requirements, and the steering lock control has to be tested in conjunction with the vehicle moving, for example, and things like that. This allows us to do that. So finally, once we have this model, and this could actually form the first component of a full-blown digital twin for a car. Now, as I'm sure you all know, the concept of a digital twin goes beyond just the electronic system and basically provides a model for the complete car in operation and allows us to do a lot of different tests on it. But this could form an electronic component for that digital twin. And we actually do have one company who's looking at, can we take this sort of idea and apply it to the mechanical side of the car as well, which is quite interesting. Early days yet. So what we can do is take this component, we can generate the tests for the top right-hand top side, which is the systematic verification, which we've been discussing so far. This is the rigorous verification and meeting the requirements using this coverage loop. But it can also then form a good comprehensive set of test vectors for random verification, where we're trying to actually find faults in the design and make sure those faults can be corrected correctly while the vehicle is in operation. And we do now have two companies who are taking this same notion and using it to create STLs, which is basically a test language which can be applied to the actual design, so it can be used to test the design while it's actually in operation. So it's for like production built-in self-tests, where as the car is driving along, and if there's an idle moment, say in one of the control systems, it can actually switch in a built-in self-test to make sure that it's still working correctly. And these kinds of tests are very, very effective to be converted into this kind of built-in self-tests and actually executed. So by basically abstracting up the requirements of how the car is supposed to operate in every sense, what we can do is provide a whole test system for the complete ISO 26262 flow and even into production tests. So just to summarize then, basically, the V model process, the systematic process, is extremely complex, as I'm sure anyone working in this field knows. You end up with huge numbers of requirements in a big Jira-like database usually. And what you have to do is make sure each one of those requirements and the implementations is fully tested and that you get a coverage report that you can actually relay back to the requirements to make sure that the full systematic process has been executed. We believe it's possible to automate this. It's fairly early days yet, but a number of companies are trying to do this using these higher level abstract test systems, which are also used in other parts of the semiconductor industry, of course, for different things. And this is really yielding some great results. It's a very clear way of modeling requirements and then automatically generating tests and providing very, very clear coverage information that relate directly back to those requirements. And what's nice about this is, having generated the test at the systematic level, you can then use the same test to run vectors for the fault simulation, random parts of the ISO 26262 process, and even into production STLs, which is really sort of starting to implement this notion of digital twin, which we're going to see, I think, much more in the industry as we move forward. And that's it, Mike and Disha.
Perfect. Thanks, Dave. We've got one question, if we can answer it quickly.
Sure.
The one question is about covering use cases concurrency. Are you doing coverage based on the test being run, or do you have a process to implement passive detection of the use cases and get coverage that way?
Yes, so a great question. So so basically the idea is to focus on the tests being run, but this can be used for passive scenarios as well. So the way this is all done is it's all, all these tests are created up front and basically can be adjusted and corrected for any kind of use case, including different passive use cases as well. And then of course the coverage is double checked when they're executed. That's it, assuming I understood that question correctly.
Yeah, you did understand it. It's a very good answer as well, very succinct. So we'll leave it there.
Okay.
Thank you. Thanks, Dave, again.
Thank you. Thanks, everyone. Morning.
Participating.